Hello everyone, I'm Jenny. I'm now working with Professor Jay Morton for my postdoc research at University of Colorado Boulder. Today I'm going to talk about some new discoveries about time lag in ionosphere scintillation response to solar storm impacts. Thanks for your interest and coming to look at my video. This is outline of my talk. First, I will give some background information about geomagnetic storm and ionosphere scintillation on GPS signal, as well as their connection in geospace. Then I will talk about the objective and the significance of my study. This is followed by the results of the time lag in scintillation response to geomagnetic storm. The results are given by GPS observations by our receiver deployed at Alaska. And in this part, we will also show some complementary results given by other receivers deployed at auroral latitudes. So finally, it's the discussion and the summary. So geomagnetic storm is the most important space weather phenomenon. It occurs when disturbed solar wind compress the Earth's magnetosphere. A storm can cause the most intense ionosphere response globally, as shown in the right-hand figures. So the irregular structures in the ionosphere during the storm, can disrupt trans-ionosphere radio signals through ionosphere scintillation. Scintillation has detrimental impacts on radio communication and satellite navigation system, as the global navigation satellite system. So here's an example that shows scintillation of GPS signals caused by irregular structures in the ionosphere. So as you may see from the upper panel, when scintillation occurs, the carrier phase to noise ratio decreases to a certain level, and this corresponds to rapid fluctuations in the amplitude and the phase of the signals. So they are called amplitude and phase scintillation respectively. So when scintillation occurs on GPS signals, we observe cycle slip in the GPS measurements, or even loss of signal log in addition to the phase error. So this may cause the degradation in GPS positioning, navigation, and timing solutions. So here we would like to give an example that provides a global view of scintillation effects during a geomagnetic storm. The results are taken from our recent publication in JGR. So what you can see from the animations is after the storm setting commencement, on the left-hand animation, the ionosphere is disturbed with outstanding expansion from the polar regions to lower latitude. And these disturbances may cause scintillation on the GPS signals. So on the right-hand animation, we can see there is a prominent increase in the position arrow extending from the high latitude down to middle latitude. So this case shows scintillation effects during a geomagnetic storm. Study of scintillation under space weather has practical interest. So here we would like to use this illustration to show the solar wind and geospace connection in GNSS data during geomagnetic storm. So as you may see, during a storm, the solar wind flow is first detected by the spacecraft orbiting at Lagrange L1 orbit. Then the solar wind flow transit to the Earth's magnetosphere and ionosphere. Finally, the ionosphere response was observed by ground-based GPS receiver and caused scintillations on the signals. So what our objective is to learn the time delay of scintillation detection on the ground since the solar wind disturbances were first detected. So to be specific, we have two objectives. The first one is to study the time shifting of solar wind data from the L1 orbit to the bullshock nose at the time of storm sudden commencement. And the second objective is to study the time lag between onset of geomagnetic storm and the scintillation detected. And those information is very important to scintillation forecast. It would provide a new insight into lead times in predicting scintillations under space weather. So this is the significance of this study. So what is the time shifting of solar wind data to the bullshock nose? So as the bullshock nose is a point close to the magnetosphere, the time shifting to the bullshock nose is to support solar wind magnetosphere coupling studies, and is estimated by this equation, and its estimation depends on the location of the observing spacecraft, the position of the bullshock nose, as well as the solar wind velocity. The time lag in this work is defined as the time delay between storm sudden commencement and the first detection of scintillation by ground-based receiver. So in this study, the criterion for detection of scintillation is given here. We use the phase scintillation index to suggest the scintillation occurrence, considering the prominent occurrence of phase scintillation at high latitudes. So this figure shows the number of geomagnetic storms in the 24th solar cycle. What you can see is the storm events reached a peak in 2015. So according to the data availability, we chose 10 storm events in 2015 for the time lag study. So here are the results of the time shifting of solar wind data. So from the upper panel, you may learn the universal time of the storm sudden commencement for the 10 storm events. So most of the storm commenced at before 12 universal time, except some events in November and December. So the lower panel shows the time shifting of the 10 storms. As you may see, the time shift is about 30 to 80 minutes. So this time information indicates the time took for solar wind disturbances detected at the L1 orbit to yield the storm onset. So for the time lag analysis, we use scintillation observation at Alaska, and this figure shows the geographical location of our scintillation receiver at Alaska. This receiver is deployed at auroral latitude. Here's an example showing the time lag in scintillation response observed by the receiver at Alaska. This case is for the 2015 St. Patrick's Day storm. The storm is the strongest one in this solar cycle so far. So the left-hand plot shows the spatial distribution of the scintillation observed during this storm. And the right-hand figure shows the time series of solar wind data and geomagnetic indices, as well as the phase scintillation indices. So what you can see from the figures is the time shifts to the bullshock nose was about 40 minutes, while the time lag between the storm onset and scintillation detected was nearly 2 hours. So in total, there's nearly 3 hours time delay since the solar wind disturbances were first detected. Uh, this is another case of the storm occurred in December. So what I would like to mention is the difference with the St. Patrick's Day storm. So the time shift of the solar wind data was at the same level, but the scintillation response for this event was observed on the second day of the storm. So the difference between the storm, so this caused a longer time lag of scintillation response. It's more than 12 hours. So the difference between the two cases indicates the time lag varies largely among the storms. So we estimate the time lag observed at Alaska for all the storm events. So here shows the results. The upper panel here shows the local time of storm sudden commencement. It suggests the receiver was most on the night side, and the middle panel indicates the scintillation was detected mostly after 20 local time on the first day of storm. According to the time of storm sudden commencement and scintillation detection, we got the time lag as shown in the uh, bottom panel. So you may see the time lag has a large range from half an hour to nearly 13 hours. So this lag information indicates the time takes for the onset of the storm to cause ionosphere scintillation on GPS signals. We also analyze the relationship of the time lag with the receiver's location. In this analysis, the receiver's location was represented in the solar magnetic coordinates. This coordinates takes the geometry of the Earth's magnetic field into account. So the key findings is supported by the figure on the right-hand figure. In the polar plots, the length of the radius indicates the time lag. So what you can see is the longer time lag is observed when the receiver faces to the sun. And the scatter plot indicates the time lag shows linear growth with the longitude change of the receiver in these coordinates. To well understand the time lag, we conduct further analysis by considering more receiver at auroral latitudes. So this work has been done recently, and a manuscript is ready for submission. So in this analysis, we take advantage of the scintillation monitor deployed at North America and Europe. Through this analysis, we got very encouraging results about the time lag. So first, it's about the latitude dependence of the time lag. As shown in the right-hand figure, in total, the time lag observed at auroral latitude is in a large range, from 10 minutes to nearly 13 hours. The most important findings is the time lag has an increased trend with the decreased latitude of the receiver. So that means when the receiver was at lower latitude, it would have a longer time lag between the storm onset and the scintillation detected. Other major findings are about the dependence of the time lag on receiver's location at the time of storm sudden commencement. So those findings were already mentioned earlier when showing the observation from the single receiver at Alaska. So here summarize the key point. So first, we found a longer time lag was observed when the receiver at lower latitude was on the day side. And another finding is about is we found there is a linear growth of the time lag with the longitude change of the receiver in the solar magnetic coordinates. Now turning to a discussion about what caused the time lags. So I think there are two major factors causing the time lag. So the first one is caused by the solar wind magnetosphere ionosphere coupling. So previous study has indicated there is a time delay between the solar energy input and the ionospheric response. So the time delay can be about 15 minutes. Another factor I think is the receiver location with respect to auroral dynamics. At auroral latitudes, there are a number of ionosphere physical processes related to scintillations, such as day-side cusp auroral transport processes of plasma patches, as well as the net-side particle precipitations. So as the Earth's rotation, the receiver's location with respect to those auroral dynamics are changing. So that could affect the detection of scintillation and the time lag observed at each receiver actually is different. So here comes a summary of the time lag study. So first, we found the time lag is in total about 1 hour to 14 hours. Those results are based on the observation at auroral latitudes. So the time lag consists of two parts. The first part is about 13 to 18 minutes, so which is the time took for the solar wind disturbances detected to yield storm sudden commencement. And the second part is about 10 minutes to 13 hours, and which is the time took for the storm sudden commencement to cause disturbances and associated scintillations. And the second, we found that the time lag depends on the receiver's location at the Earth's rotation, and it shows an increase with the decreased magnetic latitude of the receivers, and it has a linear increase with the receiver's longitude change in solar magnetic coordinates. So a longer lag was observed on the day side at auroral latitudes. Those above findings about the time lag could be ingested into models for scintillation forecast. Okay, I think that's the whole story for the time lag study. And thank you for your attention.